So I'm going to be talking about atom mapping for most of this presentation. Essentially, I'll be talking about the applications of atom mapping, what is atom mapping, and the big improvements in version 6 of Marvin. And then I'll end with a few cases which are kind of beyond atom mapping, I suppose. So, what is atom mapping? Because I'm going to be talking about it for most of this, I should probably make it completely clear what I'm talking about. Atom mapping is the process of finding finding a mapping, finding a relationship between atoms in the product, in the reactant and atoms in the product. So you can see in this example, the numbers indicate the correspondence between the atoms of the reactants and the product. That's self-explanatory. Okay, and so why would you want to perform atom mapping? There are multiple reasons. Here's a couple to start off with. You can use it as a way of assisting in classifying the reagents by whether they contribute to the product, potentially. And it's potentially of use in registration systems. Because as it is currently, whilst for small molecules, there's generally a quite vigorous registration process where you have a normalization step and the like. For reactions, there's rarely such a normalization procedure, and it's much more of a sort of free house as to how things do go about it. For example, there are even cases in the various pharmaceutical ELNs where you have the representation of nitro groups different on one side of a reaction to the other, just because there isn't much normalization going on. Anyway, given a more concrete example, you may want to use atom mapping to allow, say, for example, in this case, the THF in this case is clearly a solvent, and as you can see has no atom maps. So you might want to reclassify it like that. In this particular example, you may also notice that the reactant and product aren't in alignment as to where the reaction center is. So in principle, you can use atom mapping to also assist in aligning results, to make it clearer what has reacted in the reaction to a user. You can also, once you've got an atom-mapped reaction database, that you can use it to do more specific queries, as you then have the relationships between the reactants and the products. And I'll give you an example of why you'd want to do that on the next slide. So, for example, if I wanted to find reactions involving transforming an alkene into a cyclopropane ring, just doing a search where I search for an alkene in the reactant and a cyclopropane in the product is insufficient, because, for example, I might pull back this. I mean, it has got these features. It's got a alkene on the left-hand side. It's got cyclopropane on the right-hand side, but they're not the same atoms involved. Therefore, it's completely not what you're looking for. But with atom mapping, you can then specify that the carbons of the alkene are the carbons in the cyclopropane ring. And you can also, in principle, use, maybe as part of a registration system, you could use it to identify cases where maybe parts of a reaction appear to be missing or there's something suspect about it. So in this case, there's no atoms in the reactant side, indicating where that came from. And obviously, you can't create atoms out of nowhere. In ChemAxon's toolkit, you can access atom mapping via two methods. You can either use it from the Marvin 6.0 GUI, like that, and you can use that even when the web app has it as well. Well, obviously the web app has it, but like that. And it's also available from the API for use if you want to do batch atom mapping of large numbers of reactions. There are 3 atom mapping styles available. Complete, changing, and matching. The difference is to do with which atom. So in complete, every atom, regardless of whether it's changed in the reaction, will be assigned a label. In changing, just atoms which relate to the reaction center are mapped, and in matching, the only atoms that have a direct correspondent atom in the product are given mappings. For the rest of the presentation, I'll be using the matching style for the mappings I show. For this talk, I wanted to basically do an evaluation of the performance of it. And this actually follows on from a talk I gave about a year ago at the ACS in Boston, where we first looked at this problem. And as a result of that, ChemAxon went back and did some changes to their atom mapping algorithm, and it's now a lot better. And that's part of the reason for this talk. So we use 4 different sets to evaluate performance. One of them is a pharmaceutical ELN set, and 2 of them I think are provided by, come from Infochem. So one of them is this ChemReact database, and one of them is part of the SPRESI database. And then finally we use this 500,000 reactions which come from the US patent literature extracted by text mining. And I'll be showing examples from that set because of its publicly available, well, it's publicly available essentially, whilst the other ones are proprietary databases. So all the examples come from that. The metrics we'll use are whether you can assign a mapping to all atoms in the product. So, which essentially is a measure of recall. And then how many carbon-carbon bonds were broken. I mean, in principle, you could have a reaction that breaks carbon-carbon bonds, but it's rare in organic chemistry. Generally, you're doing reactions that make carbon-carbon bonds. And also, if there is a mapping which can be done which doesn't involve breaking a carbon-carbon bond, it's far more likely that it's the correct mapping. So that's effective, in a way, a measure of precision. So on to the graphs. So on the left bar is the version 5 result. Then you've got version 6, and I've thrown in ChemDraw for a comparison. And as you can see, the difference between version 5 and version 6 is pretty stark. There's a vast improvement. It's now a pretty competent algorithm. Very good. There's anything more to say, really. It's just like on some of the sets, it's basically managing to get mappings for the product in over twice as many cases. And then onto the carbon-carbon bonds. In this case, you now want lower because you want to be breaking as few carbon-carbon bonds per reaction as possible. And again, there's a significant improvement. So I think it's now got higher recall and it's more precise than the algorithm in ChemDraw.
Sorry, can you back one slide?
Sure.
So you only get 70% actually never work?
Right. I will go on to that later on. But you're right. I mean, from the USPTO set, I can give an explanation that as they come from text mining, some of the reactions aren't actually correct. And in fact, you might want to be, when I was doing that, in the set I put up online, actually, I used atom mapping as a way of filtering out suspect reactions. This set I did not do that on because that would be biased towards whichever atom mapping algorithm you use to do that. But yes, it is a good point. And I have an explanation for the pharma ELN set, and I have not fully evaluated why the case is in the other sets. But you're right. It is a question. Where is the other 30%? And I'll come back to that. So that's... to give a concrete example of what these graphs mean, I picked out one random example. Which one has the laser pointer on this, actually? Is it this red button? Yes, it is. So the reactants in this case are this one and this one here. And those can, yes, clearly be seen to be what coupled together to give the product on the right. Actually, there's also, I think, a ring formation as well. So in both Marvin 5 and in ChemDraw, atom maps are chosen from this triethylamine, which is, I think it's just acting as a base, possibly. But anyways, it's not contributing atoms to the product. In fact, I think both of them pick out atoms from the dioxane as well. It's completely wrong. Anyway, in Marvin 6, it gets it correct, and atom maps are only chosen from the actual reactants. And also, all atoms in the product are accounted for by the reactants. I also did a comparison of the speed. The new algorithm has not only got better results, it's also faster. And the API also offers a convenience method for doing multi-threading, making it very simple if you want to run atom mapping in parallel. And hence you can get, I guess from here, but 4 times speed improvement. This is on a quad-core machine. Obviously, if you have more than 4 cores, you get even bigger improvements. Some more difficult cases are also supported. So in this case, you have a discontinuous MCS. You have, I guess, this bit here mapping to this bit here, then this bit here mapping to this bit here, and this oxygen comes from there. It's quite complicated, but it's in this case, you just heated. Oops. Yeah, this comes from being heated up. There are still a few cases that could be improved. For example, in this case, the algorithm currently doesn't have support for cases where the stoichiometry isn't made explicit. So in this case, actually, there are two equivalents of this reacted with one equivalent of that. And that could be implemented in the future, potentially. Also, in more complicated cases, occasionally the wrong mapping is still chosen. So in this case, the reactants are this and this, but unfortunately, atoms have been chosen from that. I think it's probably to do with a bond order problem, because of in fact, from the reactants to the product, the bond order here is effectively changed from a single to a double or maybe an aromatic bond. Anyway. So anyway. We also looked into consensus methods where you try and use multiple atom mapping algorithms to see whether you can then sort of use the strengths of multiple algorithms. Including Kevin Draw 12 doesn't really make much difference. It's not a very good algorithm. But including some other ones, and you can get a reasonable improvement. You're still only at 80%. It's still far from 100%. Admittedly, you probably don't want to necessarily get to 100% because not all the reactions will necessarily be, I guess, fit for registration, but still, there's 20% remaining. What is this 20%? Just add, these are the algorithms that are used to be combined to give this consensus result from various companies. In the pharmaceutical ELN set, one of the biggest causes was basically missing reactants for common transformations. So either protections or functional group interconversions. It often just has the one reactant, one product, and then the arrow and no indication of what reagents were actually used to afford this transformation. So in principle, you can use some sort of classification software to indicate that this is a common transformation. So in this case, this is a protection or something. Yes, it's a T-block over there. And yes, there are certain common transformations. So it's potentially you could do it that way. And I'll also just add that there are cases like this one, which will be found by atom mapping, but the result is not really indicative of what's actually occurred, in that there's no indication of, it's almost like a null reaction. From the atom mapping perspective, nothing is changed, but in fact the stereochemistry is changed in this case. That's just an example of where it came from. You can get, this sort of thing can be converted via like documented structure or the like. Yes, that's true. NextMove software, one of the things we've developed is some reactant classification software, and if you combine the ones that can be classified with the ones that can be atom mapped, you can get closer to 100%. Still not 100%, but again, I'm not sure whether 100% even an ideal goal on such a set. But classification also has its own drawbacks in that, for example, when multiple reaction steps are expressed in the same reaction, that is more difficult to be done by classification than it is to be done by atom mapping. Just because of you have the confusion that multiple reactions have occurred in the same reaction that has been written down. That's right. Right. I think I might have underrun slightly, but concluding, Marvin 6.0 algorithm has a huge improvement over version 5. If you're interested in atom mapping, you should definitely try it out. There are some cases where it isn't actually as simple as finding the maximum common subgraph and then applying a chemical distance metric. And in some cases, classification algorithms can be of use to indicate that something is a chemically plausible transformation, but things have been missed out. So I'd like to thank Zolt and his development from ChemAxon for their assistance in my questions about the ChemAxon's algorithm. Some other colleagues for assistance with providing the results for the other tools. And thank you for your time, and I'll be happy to answer any questions.
Thank you very much. Do we have some questions?
Yes.
Daniel, your previous slide about classification.
Yes, this one here.
Oh, this one, right. Sorry, what's the name?
NextMove is a product we're developing in NextMove software.
It's one of your products?
Yes.
Yeah, okay. And what does it do? Explain what do you mean by classification?
So what it will do is you'll give it a certain reaction, and it will tell you that it is of, I don't know, say it's a protection reaction, or it's a Buchwald-Hartig amination reaction, and it also assign it to an ontology of, so is it a carbon-carbon bond formation reaction? Is it the protection reaction?
I follow now. Classification, I think of classification as, for example, in classify, which is actually essentially mapping. So you're using classification to mean something different from
Yes.
what I read.
Yes, it is assigning names and assigning positions in an ontology. I guess it's more of an expert system, so basically hundreds of rules for the different reaction types that you find in the literature.
Maybe I missed something. You were analyzing hundreds of thousands of reactions from patent literature as one of the examples?
Yes, so the process of evaluation is done automatically. So the carbon-carbon bond breakages and the whether all the atoms in the product are mapped can be just determined by looking at the output. So for the example I've shown here, obviously I picked those out manually from the set, but the evaluation was done automatically.
But I guess you showed examples where all the atoms were mapped, but they were mapped incorrectly. How did you determine those? Manual inspection?
So that is, I guess, a slight drawback, but if they're mapped incorrectly, it's hoped that then the carbon-carbon bond breakage metric would then be penalised on that metric if you started pulling out random carbons from a solvent to fill in the gaps in the product. Okay. So you can do very well on one metric, but then bad on the other one, and really you have to do well on both metrics to have a good atom mapping algorithm.